Right now, you are sitting on a bright, obvious planet that any smart civilization nearby should be able to notice. And yet, in all of human history, not a single verified visitor has ever arrived. No craft in the clouds, no strange beacons in orbit, nothing that forces you to say, yes, that's them. This video is about that exact uncomfortable gap, a universe that looks like it should produce neighbors, and a reality where absolutely no one has shown up. And we're going to stay locked on one question the whole time. Why has nobody come to visit us? But before we continue, please subscribe to the channel to give your support. Let's continue. How can a galaxy with hundreds of billions of stars feel so completely empty that no one has ever shown up at your front door? The short answer is the numbers are brutal, and your everyday sense of distance and speed just collapses as soon as you step outside the solar system. Start with your address. You live in the Milky Way, a spiral galaxy shaped roughly like a flat disk. That disk is about 100,000 light years across. 1 light year is a distance light travels in a year, about 10 trillion kilometers, or around 6 trillion miles. Multiply that by 100,000 and you get a span so large that normal language stops helping. The Sun, and Earth with it, sit out in the galactic suburbs, not in the crowded, star-dense core, but in a quieter band where stars are spaced far apart. Here's the key point. Just existing inside a structure this big already makes casual visits extremely hard. Even before you bring in aliens or starships or any science fiction, the bare geometry is against you. Think about how small even your own solar system is compared to that disk. And then remember, you've barely left the inner edge of that solar system so far. So you might try to shrink the problem and ask, fine, forget the whole galaxy. What about just the nearest star? How far is the closest possible neighbor who could send a ship? After the Sun, the closest star is Proxima Centauri, a red dwarf a bit over 4 light years away. In human units, that's roughly 40 trillion kilometers, around 25 trillion miles. That is the best case, the absolute minimum distance any other star system has to cross to reach you. To make that less abstract, look at something you do know, the distance from Earth to the Moon. That's about 384,000 kilometers, around 239,000 miles. The gap to Proxima Centauri is like stacking that Earth-Moon distance on top of itself well over 100,000 times in a straight line of empty space. So when people talk about just the next star over, they're talking about a jump that is already extreme even before you ask how to move anything across it. Then comes the next question. If the distance is that bad, how good are your fastest machines? How fast can you actually go? The fastest human-made object heading out of the solar system is Voyager 1. It's moving at about 17 kilometers per second, more than 60,000 kilometers per hour, roughly 38,000 miles per hour. In everyday terms, that speed is absurd. It would let you circle Earth in under an hour. But put Voyager 1 on a straight path to Proxima Centauri, and suddenly that speed looks pathetic. At its current velocity, it would need around 73,000 years to reach that star. 73,000 years ago, your ancestors were using stone tools. No writing, no cities, no science, nothing remotely like modern technology. So a one-way trip at that speed does not fit inside any reasonable planning horizon for a civilization like yours. If aliens are using Voyager-level engineering, they do not send the ship and expect a reply. They send something and know that only their distant descendants will ever see the results, if anyone at all. You might try to push back and say, well, that's just human tech. Maybe advanced aliens have something far beyond chemical rockets. Maybe they punch up towards the ultimate speed, the speed of light. Light travels at about 300,000 kilometers per second, 186,000 miles per second. As far as our best physics knows, nothing with mass can move faster than that. Even at this maximum, the size of the Milky Way still wins. Crossing the galaxy from one edge to the other at light speed takes about 100,000 years. That's the absolute best case, with no acceleration time, no obstacles, and no need to slow down at the other end. So, if a civilization on the far side of the galaxy noticed Earth today and somehow decided to send a light speed probe, that probe would reach you long before every human alive now and many generations after them were gone. Of course, real ships can't reach light speed, so let's be generous and talk about 10% of that, zero point 0.1 times the speed of light. That's 30,000 kilometers per second, about 19 million miles per hour, way beyond anything humans can currently build, but still allowed by physics. At that speed, crossing the full width of the galaxy now takes about 1 million years. That's not a mission, that's a geological era. Even jumping just 4 light years to Proxima Centauri at 10% light speed still takes over 40 years, which means you need technology that can keep a crew or a machine functioning reliably for a human lifetime in deep space. So here's the next problem. If space is this large and speeds are this limited, what does that do to the idea of regular visits, of star-faring civilizations constantly bumping into each other? You get a galaxy where even friendly, curious species live inside huge, isolated bubbles defined by how far they can travel in a reasonable time. The overlap between those bubbles is tiny. Most of the time, no one else's reachable zone intersects yours. Once you put all of this together, the silence you see around you stops being a mystery and becomes the expected baseline. The Milky Way is a disk roughly 100,000 light-years wide. Your nearest star neighbor is more than 4 light-years away. Your fastest probe would need tens of thousands of years to get there. Even with physics-breaking levels of engineering compared to what you have now, you still pay tens of thousands to millions of years to cross real galactic distances. Under those conditions, dropping by is not a normal behavior, it's an extreme outlier. The universe is not ignoring you, and it is not sending a message by staying quiet. On these scales, with these speeds, the natural state of the galaxy is that civilizations, if they exist, almost never meet face to face. Visits are rare by design, not because anyone chose it, but because the geometry and the speed limit make it that way. So if just the size of space and the hard cap on speed already make visitors incredibly unlikely, what happens when you add another constraint, the energy problem, and ask how much power your civilization like yours would actually need to even try to cross those distances? How powerful do you think your civilization really is on a cosmic scale? Because from the universe's point of view, you're not a spacefaring adult. You're a toddler playing with firecrackers at the bottom of a gravity well. There's a simple way scientists talk about this, called the Kardashev scale. It's just a rough rating system for how much energy a civilization can control. Type 1 means you can use basically all the power available on your home planet. The sunlight hitting it, the wind, the tides, the geothermal heat, everything. Type 2 means you've gone bigger. You're using most of the power output of your star, maybe with huge structures around it. Type 3 is full galaxy mode. You're using the energy of billions of stars. Now, here's the reality check. Humanity is not even at type 1. You're somewhere around 0.7 on that scale. In other words, you're grabbing maybe 1 to 2% of the energy your planet could, in theory, provide. You don't control weather, you don't harness every watt of sunlight, you still burn fossil fuels and argue about power grids. On paper, you're advanced, but in Kardashev terms, you're low level. So here's the first punchline. If most civilizations stall where you are now, below type 1, they never build the kind of energy surplus you need to throw starships between stars like it's no big deal. They stay busy just running their planet, feeding their population, keeping the lights on. On that budget, interstellar travel isn't normal transport, it's an extreme luxury. That leads to the next question. What are you actually flying today, and how does it compare to what you'd need? Right now, your main tool for getting off the ground is chemical rockets. A modern heavy-lift rocket, the kind that takes big payloads into orbit, can push something up to speeds around 11 kilometers per second, roughly 40,000 kilometers per hour, about 25,000 miles per hour. That's enough to escape Earth's gravity, which feels impressive. But look at that same speed against the speed of light. 11 kilometers per second is about 0.0037% of light speed. Not 1%, not half a percent, a few 10,000ths of the maximum speed the universe allows. Even 1% of light speed, around 3,000 kilometers per second, roughly 1.9 million miles per hour, would be about 270 times faster than anything you've actually flown. So, chemical rockets are great for jumping into orbit, great for hopping around the solar system, and almost useless for interstellar travel. The fuel requirements explode, the travel times go off the chart, and every kilogram of payload becomes painfully expensive. If aliens out there are stuck with similar chemistry, they stay in their home system too. They don't visit you not because they can't do math, but because the math tells them it's a bad deal. You might respond with, fine, then the real players use advanced drives, fusion engines, laser sails, the big sci-fi ideas. And yes, people have looked at that seriously. Concepts like fusion drives or laser-pushed light sails, similar to the breakthrough Starshot proposals, aim for speeds up to 20% of light speed, 0.2 times c. That's around 60,000 kilometers per second, tens of millions of miles per hour. Now you're talking about crossing a light year in a few years instead of decades. But here comes the next hard wall: energy. When you accelerate even 1 kilogram of mass to 20% of light speed, you're dumping an enormous amount of energy into it. We're talking on the order of 10 million billion joules for each kilogram. In more familiar terms, that's comparable to thousands of megatons of TNT for every single kilogram of your ship. Not the whole mission, just each kilogram you want moving that fast. Think about what that means. A probe of only 100 kilograms, which is small, carries kinetic energy similar to a ridiculous fraction of your entire nuclear arsenal. A crewed ship with shielding, life support, and structure quickly becomes a flying disaster level if anything goes wrong. And that's just the launch. You also have to slow the ship down at the destination, or it just screams past the target star system and keeps going into deep space. So, you're in a situation where every serious interstellar mission becomes a planetary-scale energy project. Not this year's space budget. More like, let's allocate a noticeable chunk of all the energy our species uses for decades. That's what it takes to push matter close to light speed, even with advanced propulsion. Now raise the stakes again and ask, what about civilizations much stronger than you? Close to Type 2 on the Kardashev scale, using most of their star's output, maybe with huge collectors in space. Surely they can travel all they want, right? Even for them, physics does not relax. Accelerating large ships to high fractions of light speed is still expensive. It just hurts them less. For a Type 2 civilization, launching a big interstellar crewed mission might feel like you deciding to spend your entire country's yearly energy budget on one single truck delivery. Technically possible, but you don't do that every day. You do it for rare, vital reasons, after a lot of planning, and you probably send something as small and efficient as possible, not giant luxury cruisers. So this leads to a very different picture of aliens visiting. The math doesn't forbid it, it just makes it rare, targeted, and expensive, even for the big players. Maybe they send small probes, not giant ships. Maybe they send one mission every few thousand years, not a stream of tourists. Most of the time, they invest their energy into closer, higher return projects, mining their own system, building infrastructure, running mega-scale computing, whatever their priorities are. So here's the deeper point. If most civilizations never climb high on the Kardashev ladder, or they only just reach Type 1 or Type 2 and then hit limits or crises, then star hopping stays the exception. It's not what everyone does once they're advanced. It's a niche activity for the rare few who are rich enough, stable enough, and stubborn enough to pay the insane energy bill. From that perspective, your quiet sky is not a paradox. It's the baseline. You live in a galaxy full of Kardashev babies, including yourself, stuck close to their home stars, using almost all their power just to survive and grow. The default state is that nobody has the spare energy to casually cross 40 trillion kilometers to tap on your window. So, if even energy-rich civilizations struggle to justify that kind of effort, the next question is, how many planets out there even make it far enough along this road to try, instead of getting stuck as worlds full of microbes, flares, and bad weather that never build starships at all? If the galaxy is full of planets, why aren't you drowning in neighbors by now? You keep hearing that we found thousands of worlds, so the silence should feel strange. But when you look closely at what those planets are actually like, the silence starts to make sense very fast. First, the raw count. Since the 1990s, astronomers have been stacking up exoplanets, planets around other stars. By 2025, NASA's catalog passed 6,000 confirmed worlds, and that's just the ones we can see with today's instruments. Kepler, the telescope that stared at one patch of sky for years, found thousands by itself, and hundreds of those sit in what we call the habitable zone, the range of distances where liquid water could exist on a planet's surface. On paper, that sounds great. Lots of planets, lots of habitable zones, so you might think, okay, the galaxy's packed, there must be Earth 2.0s everywhere. So here's the problem. In the habitable zone is just step one in a long filter, and it's the easy one. It only tells you about temperature, not about everything else that actually makes a world friendly to life for billions of years. Being in the right band around a star doesn't guarantee oceans, continents, or breathable air. It just means you're not instantly a frozen ball or a vaporized rock. If you stop the analysis there, you'd be wildly overestimating how many real, comfortable, long-term homes are out there. So the next question is, what are these planets actually like when we dig into the details? The answer is, most of them are nothing like Earth. We see hot Jupiters, giant gas planets that orbit so close to their stars that their year is a few days. Their atmospheres are superheated, and parts of them may literally be boiling off into space. We find super-Earths with several times Earth's mass where we don't even know if they have solid surfaces you could stand on, or crushing atmospheres that act more like mini-Neptunes. We find mini-Neptunes, worlds wrapped in thick gas envelopes, deep atmospheres, high pressures, not places where you build cities and launch pads. A lot of the planets we found don't orbit stars like the Sun at all. They orbit red dwarfs, small, cool stars that burn for trillions of years. That sounds stable until you realize many red dwarfs are hyperactive, throwing off powerful flares, X-rays, and charged particle storms. If your planet sits close enough to stay warm, it sits close enough to get blasted over and over by radiation bursts. That's more like trying to develop a high-tech civilization under constant space weather attacks than peacefully evolving under a quiet, steady sun. The basic message is simple. Most planets are weird, extreme, or outright hostile, not calm blue marbles. You might try to narrow it down and say, okay, forget the whole catalog. What about our nearest maybe habitable neighbor, Proxima Centauri b? That one should be a decent test case. Proxima b orbits Proxima Centauri, the closest star to the Sun. It sits about 0.05 astronomical units from its star, roughly 7.5 million kilometers, around 4.7 million miles. That's about 20 times closer to its star than Earth is to the Sun, and it's even closer in than Mercury is in our own system. Now add the star's behavior. Proxima Centauri is a flare star. It throws violent outbursts that flood its surroundings with high-energy radiation. A planet that close is getting hammered. Its atmosphere, if it ever had one like Earth's, might be stripped or heavily altered. The planet is probably tidally locked as well, showing one face to the star all the time. So one side is in permanent day, the other in permanent night. You can, in theory, still have some habitable zones in between, but it's not the smooth, global, mild climate you enjoy on Earth. This is your nearest maybe okay world, and already habitability is iffy at best, not great, let's move in. So what are the bigger lessons from the latest observations, the ones coming in now from powerful telescopes like JWST, the James Webb Space Telescope? In 2025 and around that time, it started taking spectra of exoplanet atmospheres, including interesting targets like K2-18b and planets in the TRAPPIST-1 system, such as TRAPPIST-1e. These are some of the best candidates for studying what habitable really looks like in practice, and what we see is not a universe full of Earth clones. For some of these planets, the atmosphere looks strange, maybe rich in hydrogen, or showing signs of potential greenhouse runaways. Others might be ocean worlds with enormous deep oceans and no continents, which matters a lot for climate cycles and long-term stability. Some may be losing their atmospheres under stellar radiation. The key point is, even when a planet sits in the right temperature zone, that still doesn't guarantee a stable, surface-friendly, life-friendly environment. You can land in that zone and still end up with a steam bath, an ice shell over high-pressure water, or a toxic chemical mix. So you have to ask a harder question. How many planets can stay in a sweet spot not just for a few million years, but for billions of years, long enough for life to start, adapt, and then climb all the way up to a civilization that can build radios, rockets, and maybe starships? Earth took over 3 billion years to go from simple cells to complex animals, and then only in the last tiny slice of that did you arrive at a species that figures out physics and engineering. That whole time, the planet needed to avoid total sterilization, runaway climate catastrophes, and permanent atmosphere loss. When you overlay that requirement on what we're seeing, the odds shrink fast. Many planets are in harsh radiation environments. Many have unstable climates. Many orbits may drift over time, moving planets in and out of habitable zones. On top of that, you need enough heavy elements to build rocks, continents, and technology. You need plate tectonics or some other mechanism to recycle carbon and stabilize climate. And you need a star that keeps behaving itself for billions of years straight. So even though 6,000 plus exoplanets sounds like a big number, and the real total in the galaxy is probably in the hundreds of billions, the subset that can host long-term, stable, surface civilizations that also reach spaceflight is almost certainly much smaller. You're not selecting any planet with the right temperature for a while. You're selecting planets that basically pull off the same multi-billion year balancing act that Earth did, under all the random hits and chaos of cosmic history. From that angle, the lack of visitors becomes less mysterious and more like what you'd expect. Yes, there are lots of planets. Yes, some of them sit in habitable zones, but the number of worlds that stay nice and stable long enough and then actually produce a technological species and then keep that species alive long enough to start interstellar projects is probably tiny compared to the raw planet count. You might simply be sitting on one of the rare winners in a galaxy mostly filled with planets that either never got past microbes or never stayed calm enough for anything smarter to take over. So, if the universe is full of planets, but very few of them ever host high-tech civilizations, the next step in the chain is obvious. Maybe life itself is common, but the jump from slime to starships is brutally hard, and that's the real reason almost no one is out there with the ability to come visit you. How can a planet be alive for billions of years and still spend almost all of that time without anything that can build a radio, a rocket, or a computer? If you want to know how common alien visitors should be, you have to look at your own timeline first, and that timeline is a warning. Life on Earth goes back maybe 3.5 to 4 billion years. That's more than 3/4 of the planet's history. But complex animals, the kind you see in fossils that look like recognizable creatures, only really show up in a big way about 540 million years ago, during what's called the Cambrian explosion. That means for roughly 80% of Earth's movie, nothing with eyes, legs, or a brain like yours was around. Intelligent tool-using primates appear only in the last few million years. Modern humans with language and culture, a couple of 100,000 years. Radio, rockets, digital tech, barely the last 100 years. So here's the first red flag. If you hit replay on Earth over and over, there is no guarantee you get that last tiny slice with technology again. Most of the time, you just get a long, slow, simple story that never reaches spaceflight. If this is a typical pattern for life-bearing planets, then life and technological civilization are two different categories, separated by billions of years and a lot of evolutionary luck. That leads to the next uncomfortable point. What was actually happening on Earth during all those billions of years before animals and people? The answer is simple and a bit depressing. Microbes ran the place. Single-celled organisms dominated for most of Earth's history. No forests, no animals, no intelligent observers, just oceans and microbial mats doing chemistry. Those microbes were not doing nothing. They completely changed the atmosphere. The Great Oxygenation event around 2.5 billion years ago was driven by photosynthetic microbes dumping oxygen as a waste product. That oxygen was toxic to many earlier life forms, but it eventually made complex life possible. So yes, microbes can reshape a planet in deep time, but they do not build telescopes, rockets, or starships. They don't care about the stars at all. If that pattern is common, then most living planets in the galaxy might be covered in slime, films of bacteria, clouds of single-celled plankton, maybe a few simple multicellular things. From orbit, they might show signs of chemistry that screams biology, but on the ground, there's no city, no launch pad, no radio tower, just a global biosphere that never makes the jump to engineering. This is why astronomers talk about two different targets: biosignatures and technosignatures. A biosignature is any sign that a planet's atmosphere or surface has been altered by life. That might mean oxygen and methane existing together when they should have reacted away, or other weird combinations that are hard to explain with geology alone. With big telescopes, you can look at starlight passing through a planet's atmosphere and break it into colors to see those hints. A technosignature is something else entirely. That's a sign of technology, not just biology. Radio signals that don't match natural sources, bright laser pulses, waste heat from huge artificial structures, things that require a species pushing around large amounts of energy on purpose. To show up as a technosignature, life has to go from doing chemistry to doing engineering. It has to evolve not just intelligence, but tools, machines, industry, and a culture that sustains all of that. That jump is much harder than just life exists. Microbes don't accidentally build radios. Complex animals don't automatically discover physics. You need a very specific chain of events: nervous systems, problem solving, social behavior, language, technology, and then a long period where that technology doesn't wipe you out. And all of that has to happen before your star or your planet's climate makes things impossible. So, what do current observations tell you about how many planets might have made that jump? For a few decades, people have been running SETI projects, the search for extraterrestrial intelligence. They point radio telescopes at stars and look for narrow, structured signals that stand out from background noise. More recently, projects like Breakthrough Listen have scanned thousands of nearby stars over wide ranges of frequency, using some of the biggest radio dishes on Earth. So far, the result is no confirmed technosignature. That doesn't prove there is nobody out there, because your search is still tiny compared to the size of the galaxy. You've looked at a small number of stars for limited times in certain bands of the spectrum. But it is a data point. If space were full of very loud, very wasteful civilizations blasting out strong, continuous radio beacons in all directions, you probably would have picked up something obvious by now. The fact that you haven't suggests that, at least in your neighborhood, such civilizations are not common. Put that together with Earth's long microbial history, and you get a simple but harsh picture. Life itself might be easy. Give a planet liquid water, useful chemistry, and some time, and microbes might show up often. But the jump from microbes to minds that can build technology, and then from technology to stable, long-lived, space-capable civilization looks rare and fragile. In that scenario, the galaxy could be full of biology and almost empty of engineering. Clouds of alien bacteria might be floating in distant oceans. Strange microscopic ecosystems might be thriving under ice shells or in thick atmospheres. But very few planets ever reach the point where visit another star is even a concept that anyone can think about, let alone execute. If that's true, then the silence around you is exactly what you should expect. No one is ringing your doorbell because almost no one ever builds a doorbell. For most life in the universe, there is no radio bubble, no rocket launch, no probe leaving the home system. There is just a long, slow cycle of growth and extinction that never leaves the planet's surface. So, if technological civilizations are that rare and that fragile, even on worlds that do manage to produce them, you have to ask the next darker question. When they finally light up, how long do they actually stay visible before something, either in space or at home, wipes them out again? Here's the next problem nobody likes to think about. Even when a civilization finally appears, it might not stay around very long, at least not on the timescale the galaxy cares about. Start with your own footprint. For most of human history, Earth was completely dark and silent from the outside. No big artificial signals, no strong radio, no radar, nothing that stands out across light years. Only in the last century or so have you started leaking powerful radio and TV transmissions into space, plus radar blasts from things like air traffic control and planetary radars. All of that forms a kind of expanding sphere, a radio bubble, centered on Earth. Right now, that bubble is only about 100 light years in radius. That means any star farther away than that is still seeing you as you were before radio, before rockets, before modern industry. 100 light years sound huge, but set it against the Milky Way, which is about 100,000 light years across. Your detectable sphere is 1,000 times smaller than the diameter of the galaxy. In linear terms, that's like a 1 millimeter dot on a 100-meter line. Easy to miss unless you're looking right at it at exactly the right time with the right tools. So your "here we are" signal is both weak and recent. It hasn't had time to reach most of the nearby stars, let alone the entire galaxy. Any civilization outside that small bubble literally cannot know you exist yet from your own leakage. If they're waiting for a clear sign before paying attention, they're still waiting. Now compare the ages involved. The Milky Way is more than 13 billion years old. Earth has existed for about 4.5 billion years. Complex multicellular life, things like plants and animals, only show up in a big way around 500 million years ago. Human civilization, in the sense of cities, writing, organized states, is only a few thousand years old. High technology with electricity, computers, radio, and spaceflight is just the last 100 or so. Even if a technological civilization manages to survive 1 million years, which is far beyond anything you have managed so far, that 1 million years is still a tiny sliver compared to the galaxy's age. 1 million out of 13 billion is less than a 10,000th. Put differently, you could have thousands of separate civilizations, each lasting 1 million years, scattered across the galaxy's history, and most of them would never overlap in time. Two fireflies that light up millions of years apart simply never see each other, no matter how bright they are. Then add in the universe's habit of hitting the reset button. Space is not calm and safe on long timescales. Massive stars explode as supernovae. These explosions release huge amounts of energy, including high-energy radiation. A supernova within a few tens of light years can damage a planet's ozone layer, change climate, and increase mutation rates. Gamma ray bursts are even more extreme, brief but incredibly powerful jets that can affect regions thousands of light years across if a planet sits in the beam. Over billions of years, these events go off again and again in different parts of the galaxy. Each time, they can sterilize planets, strip atmospheres, or at least force life to start over from a simpler state. Add in other disasters like close passes by other stars, big impacts from asteroids or comets, and slow changes in a star's output, and you get a picture of a galaxy that occasionally wipes out or heavily disrupts complex life in random patches. So even if the galaxy produces civilizations regularly, many of them might be cut short. Some get wiped out before they ever reach spaceflight. Others might reach a high level, then get hit by an external disaster or by their own technology and disappear. On very long timescales, these are like brief flashes of activity scattered through time, not permanent fixtures. Now, put all of this together and ask, what has to line up for aliens to visit you right now? They need to have evolved recently enough that they still exist. Their civilization has to still be in a phase where they can launch interstellar missions, not long collapsed or transformed into something undetectable. They also have to be close enough, within a few tens or maybe a few hundred light years, so that travel is even remotely feasible with any reasonable technology. On top of that, they have to know you're here. That means either they are extremely good at spotting life and techno signatures at long range, or your own radio bubble has already reached them and they happen to be listening. If they're hundreds or thousands of light years away, your signal hasn't arrived yet, so they have no direct evidence you're worth visiting. And even if they notice you, they then have to decide that you're important enough to spend the energy on a mission, and that mission then has to survive the journey. Each one of those conditions cuts down the odds. Long-lived, stable civilizations are rare. Being close in space is rare. Overlapping in time is rare. Noticing each other in a very short detection window is rare. Committing to an actual visit is rarer still. Multiply all those small chances together and you get a situation where physical meetings are the exception, not the rule, even if the galaxy has produced many civilizations over its lifetime. This leads to a possibility that sounds bleak but fits the data. You might be living in a quiet interval. There could have been advanced species in your region of the galaxy tens or hundreds of millions of years ago. They might have built things, explored, even gone interstellar in their own way. But they are gone now, wiped out or transformed into something that leaves no obvious trace for you. Future civilizations might rise millions of years after you're gone, under different stars in different systems, and they will not know you were ever here, except maybe as faint chemical traces in old rocks. From your point of view, the galaxy then looks empty and silent. No ships, no clear signals, no obvious megastructures. But that doesn't mean nothing ever happens. It just means you almost never get two spacefaring species existing at the same time, close enough with the right technology and with enough overlap to see each other or meet in person. Most of the time, one lights up, burns for a while, and then fades before the next one appears nearby. So when you look up and see a quiet sky, you might be seeing not a permanent emptiness, but a temporary darkness between brief, scattered bursts of civilization. And if that's the case, then the next question is even sharper. Maybe the universe also has boss fights built in, great filters that most species never pass, and that decide which tiny fraction, if any, ever gets the chance to last long enough to travel the stars. If civilizations really do blink on and off like fireflies, the obvious question is, why do so many of them go dark? The idea behind great filters is simple and brutal. Somewhere between simple chemistry and a long-lived spacefaring culture, there are a few steps that are so hard most planets never get through them. Start with the steps you've already cleared, or at least you think you have. Life had to start at all, turning basic chemistry into the first self-copying molecules in cells. On Earth, that seems to have happened fairly early, within the first few 100 million years. Then came the jump to complex cells, eukaryotes, with nuclei and internal structures. That took well over 1 billion years to show up. After that, multicellularity, cells sticking together in stable, organized bodies, took hundreds of millions of years to really take over. Then, much later, intelligence capable of tools, language, and planning emerged in one narrow branch of animals. Each of those steps took a huge amount of time, even on a planet that had liquid water, decent stability, and billions of years to play with. That's a hint they are not trivial. They didn't happen as soon as possible, they happened after long delays. From a great filter perspective, each one is a candidate choke point. Maybe most planets get stuck before life. Maybe lots of planets get life, but almost none evolve complex cells. Maybe complex cells are common, but multicellular animals are not. Maybe brains good enough for technology show up only rarely. You only see your own success path because you're sitting at the end of it. You don't see the trillions of dead ends where evolution stalled at microbes, or at simple worms, or at social animals that never invent writing. The fact that each step took billions or hundreds of millions of years on Earth suggests they were not guaranteed. If any one of them really is a low probability event, then most planets never get to a stage where visit another star is even on the menu. But the uncomfortable part of the great filter idea isn't just behind you, it might be in front of you. Past filters are scary, future filters are worse because you're heading straight toward them. Look at your own risk list. Self-inflicted extinction is no longer theoretical. Nuclear weapons exist. Engineered pathogens are possible. A global war or a deliberate or accidental release of something highly infectious and lethal could kill billions and wreck civilization fast. Runaway climate disruption is another live candidate. You are currently pushing carbon dioxide levels higher at a rate that is extreme in geological terms. That changes temperatures, sea levels, and weather patterns. If you push it far enough, you destabilize food systems, trigger mass migrations, and strain systems. At some point, that can tip a global civilization into collapse, even if some humans survive. A crashed civilization may not climb back to high technology easily, especially if the easiest coal and metal deposits are already used up. Then there are technology accidents you don't fully understand yet, like uncontrolled AI systems or other advanced tech. A misaligned powerful system or a chain of failures in tightly connected global infrastructure can cause damage on scales past anything in history. These are not far future sci-fi toys. These are topics governments and researchers argue about right now because they see the risk. Now think about how this looks from far away. Earth is already broadcasting a signature that says this place is in a dangerous transition phase. Rising CO2 levels leave a clear spectral fingerprint in the atmosphere that we could, in principle, detect on a distant planet with good enough telescopes. Industrial pollutants, if concentrated enough, also leave unusual markers. To an advanced observer, Earth's atmosphere would not look like a quiet, stable biosphere. It would look like a system being rapidly perturbed by an industrial society. From their point of view, that might not look like a promising member of the Galactic Club. It might look like a world in the middle of a stress test, where the outcome is unknown. Some might choose to wait and see if you survive your own great filters before considering any contact. Others might categorize you as likely to crash and never come back. In both cases, no one shows up now. There's also a big observational hint that supports the idea of strong filters. When astronomers look at galaxies, including our own, they do not see obvious signs of galaxy-spanning engineering. We don't see large numbers of stars whose light is heavily blocked and re-emitted as heat in a way that would scream Dyson swarm. We don't see whole galaxies dimmed or reshaped by massive artificial structures. On large scales, galaxies look like physics, not like visible industry. That leaves you with two main options. Either super advanced civilizations are extremely rare, meaning very few species ever make it past the key filters and grow to type 2 or type 3 on the Kardashev scale, or those that do survive and become powerful choose to not expand in loud, wasteful ways that would be easy to spot. Both options are bad news for the idea of friendly neighbors dropping in all the time. If almost everyone fails a filter early, before high tech, then the galaxy is mostly full of simple life, maybe some complex ecosystems, but almost no one with starships. If many reach high tech, but then hit a future filter shortly after, wiping themselves out with war, climate, or accidents, then the galaxy is mostly full of ruins and brief flashes that never last long enough to build galaxy-wide projects. Either way, the number of civilizations that both survive and choose to build big, visible, expansionist infrastructure is tiny. In that kind of universe, no one has visited stops being a surprise and turns into the default expectation. You don't see visitors because almost no one survives long enough and chooses to become a regular interstellar traveler. Most fall at some step in the gauntlet. You happen to be in the short window where you've just noticed the danger but haven't found out yet if you're one of the few that gets through. So if deadly filters, both natural and self-inflicted, already make advanced civilizations rare, there's another angle you have to face. Even if some survive and build technology, your tools for noticing them may be far too weak and your search is far too narrow for you to realize they're already talking. You look out at the sky and say, "It's so quiet, there's probably no one there." But that assumes you're actually good at listening. You're not. Right now, you are almost deaf on cosmic scales. Start with the basic physics that works against you, the inverse square law. When you transmit a radio signal, the energy spreads out as it travels. Double the distance, and the strength of that signal per square meter drops to a quarter. Multiply the distance by 10, the strength drops to 1/100th. By the time you're talking about hundreds or thousands of light years, even a powerful transmitter, running at megawatts, has been smeared over a sphere so large that at your end, it looks like background fuzz. That's why your own leakage is such a non-event for the galaxy. Old TV broadcasts, radar pings, radio chatter, all of that spills into space, but it spreads out, weakens, and quickly sinks into the noise. With the kind of receivers you have today, that stuff becomes essentially undetectable after a few dozen light years. So when you worry that you've been shouting your presence to the cosmos for a century, the truth is you've barely whispered beyond your neighborhood, and even that whisper fades fast. Now look at what you've actually done to search for anyone else. Under the label SETI, the search for extraterrestrial intelligence, you've pointed radio telescopes at the sky and looked for narrow, artificial-looking signals. But the reality is, you've only managed to scan a few thousand stars in any serious way, and only across specific frequency bands for limited times. Projects like Breakthrough Listen are the most ambitious so far, using big dishes to monitor over 1,000 targets in detail. That sounds impressive until you compare it to the hundreds of billions of stars in the Milky Way. On galactic scales, that effort is tiny. It's like standing in one city block, listening for a specific kind of whisper, while the galaxy is the size of a continent. You checked a few places, on a few nights, on a few channels, and you didn't hear anything. That does not let you conclude the continent is silent. It just tells you your current search cone is narrow and shallow. On top of that, you are not listening in a quiet room. Space is full of natural radio sources. Pulsars, which are rotating neutron stars, emit regular radio pulses. Quasars and active galactic nuclei blast out radio waves from the regions around supermassive black holes. Even the Milky Way itself glows in radio frequencies, thanks to charged particles spiraling in magnetic fields and other diffuse processes. All of this creates a complex background. So any alien signal you're hoping to find has to stand out against that mess. It might be sitting right next to a pulsar's emission in frequency space, or buried under fluctuations you classify as noise or interference. Your algorithms throw away a lot of spikes and weird patterns because they look like local radio pollution, electronics glitches, or natural astrophysical sources. An engineered signal that doesn't fit your expectations very clearly could easily get tossed into the uninteresting bin. Then there's your blindness and time. You don't stare at one star continuously for years. Most surveys jump from target to target. You look at a star for maybe a few minutes, maybe a few hours at most, on certain days, then move on. But there's no law that says an alien civilization, if it's sending beacons at all, has to send them continuously. A tight, energy-efficient signal might only turn on briefly, say 1 minute once a year, or in some other pattern tied to their calendar or science goals. In that situation, timing is everything. If they send for 60 seconds on one particular day, and you happen to watch that star for 30 seconds 6 months earlier, you get nothing. You mark the star as quiet and never realize you just missed your only shot for that year. To really be confident, you'd need to watch thousands or millions of stars across many frequencies nearly all the time. You're nowhere near that capability today. Put all of this together and ask what a null result actually means. Weak transmissions fade fast. Your listening covers a tiny fraction of the sky, a tiny fraction of the spectrum, and a tiny fraction of the time. You're competing with loud natural radio sources. Your algorithms are tuned for certain kinds of signals, and you ignore or discard a lot of anomalies. Under those conditions, "we haven't seen anything" is exactly what you should expect, even if the galaxy has a moderate number of technological civilizations. So, no signal yet does not equal no one is transmitting. It means your current setup, your telescopes, your strategies, and your assumptions are only giving you a very narrow view. You're like someone standing in a noisy factory, listening through a cheap headset, trying to catch a specific whisper coming from kilometers away. When you don't hear it, the honest conclusion is not "no one is talking," it's "this is a terrible way to listen." And that changes how you should read the silence. The universe may well be full of signals you're not tuned to, either because they're too faint by the time they reach you, or because they're using frequencies, modulation schemes, or time patterns you rarely check. There could be a civilization pinging a tight laser beam between two nearby stars, or sending narrow-band radio bursts on a schedule you haven't thought to monitor. From your point of view, that all blends into nothing. If that's the situation, then the lack of a clear, dramatic hello tells you more about your own limits than about the true state of the galaxy. You're not hearing much because, for now, you're almost deaf. And if your instruments and methods are still this immature, then your ability to find something even harder, actual planets with visitors, probes, or artifacts, is even weaker. So if you're barely hearing the loudest possible version of a message, what does that say about your chances of spotting something subtler, like a small robotic probe passing through your system, or visitors using methods you're not watching for at all? You talk about alien planets like you've already mapped the galaxy, but the truth is you're still at the stage of just proving planets are common at all, not actually finding the specific places where visitors could come from. Start with how you even detect most exoplanets right now. You mainly use two tricks: the transit method and the radial velocity method. The transit method looks for tiny dips in a star's brightness when a planet passes in front of it. The radial velocity method watches the star wobble slightly because a planet's gravity tugs on it. Both of those methods are heavily biased. They're best at finding big planets that are very close to their stars, circling fast, causing big dips and big wobbles. So what do you see most? Hot Jupiters, giant gas planets whipping around their stars in a few days, super-Earths and mini Neptunes, heavier and larger than Earth, often hugging their stars on tight orbits. Those are the easiest to spot because they block more light and yank harder on their stars. Small Earth-sized planets at Earth-like distances are much harder. The signal is weaker, the transits are rarer, the wobble is smaller. So your catalog is strongly skewed toward big, close, and weird worlds, not toward temperate, quiet Earth clones. That's a bit like trying to understand human cities by only noticing the tallest skyscrapers that happen to be within 1 kilometer of your front door. You'd conclude that city means one absurdly tall building right next to me, because your method barely picks up anything else. That's where exoplanet science is. You see the loud, obvious cases first, and everything else is undersampled. Now look at the missions that convinced you planets are everywhere. The Kepler Space Telescope stared at one small patch of sky for years, monitoring around 150,000 stars for transits. From that one patch, it pulled out thousands of planets. That told you that statistically, planets are common. Later, TESS, the Transiting Exoplanet Survey satellite, started scanning almost the whole sky, focusing on brighter and closer stars, and found many more. But here's the catch. Neither of those missions did a full, detailed survey of all nearby sun-like stars. Kepler only watched the specific region, and it missed planets that didn't transit from its line of sight. TESS gives you candidates, but many systems are still not mapped in depth. There are plenty of stars in your local neighborhood for which you have no complete picture. You don't know how many Earth-sized planets they have, how many lie in habitable zones, or what their atmospheres look like. So when you say, if there were aliens, we'd know which systems to watch, that's just not true yet. For most stars, you don't even know if they have planets that could host life, let alone advanced civilizations. Next, think about what's coming. The Nancy Grace Roman Space Telescope is designed to push exoplanet detection much further, especially for planets at Earth-like distances. Using techniques like microlensing and high-precision imaging, it's expected to add huge numbers of new worlds to your list, potentially over 100,000 extra exoplanets, along with a much sharper map of the Milky Way's center region. That will change your picture a lot. Today's catalog will look small, like an index or a teaser compared to what those next-generation surveys will reveal. Right now, you're proud of 6,000 confirmed planets. In a few decades, that might look like saying, we know the names of a few streets in one district, when the real city is sprawling for kilometers in every direction. If you're only just moving from planets are common to here are detailed maps of thousands of planetary systems, it's way too early to claim you've ruled out visitors with any confidence. You don't yet have a full phone book of possible homeworlds, only a rough draft. There's another layer to this. You've only recently started thinking carefully about where alien civilizations would actually have the best chance to notice you. One example is the Earth Transit Zone. That's the thin band of positions in the galaxy where a distant observer would see Earth transit the Sun, the same way you watch exoplanets transit their stars. From those stars, aliens could have detected Earth as a small regular dip in their sun-like star, and maybe analyze its atmosphere for signs of life or industry. Only in the last few years have astronomers begun to systematically list those stars and treat them as special targets for SETI and exoplanet follow-up. Before that, your searches were more scattershot. You were pointing instruments all over the place without focusing on the most likely vantage points where someone could know you exist. That means your odds of catching a deliberate signal or spotting a probe were even lower than they had to be. And remember, this is just about finding planets and possible senders. Finding actual visitors, like probes or artifacts, is much harder. To do that well, you need to know which systems are promising, which stars are likely homes for long-lived advanced civilizations, and then you'd need to search your own solar system in detail for anything odd, unusual orbits, strange objects, unnatural materials. Right now, you don't even have a complete catalog of all small rocks in your own backyard, let alone tiny artificial probes. So ask the key question. If you don't yet have a complete map of nearby planetary systems, if you're only starting to prioritize vantage points like the Earth Transit Zone, and if your surveys of your own system are incomplete, what should you expect to see? The honest answer is you should expect to see almost nothing. Not because nothing is there, but because you're in the early learning the street layout phase of galactic exploration. You've just gone from we know only our own planets to we know planets are everywhere. You haven't yet reached we know which stars have Earth-like worlds, which ones might host advanced civilizations, and where to look for their hardware. You're still drawing the first decent draft of your star map. In that situation, no visitors detected is not a shocking mystery. It's exactly what you'd predict. You're not missing obvious lines of alien traffic, you're just not looking in a targeted, informed way. You don't know which neighborhoods to watch, which systems to scan for strange comets or unusual objects, or where a cautious civilization might park a probe to watch Earth quietly. So instead of reading the lack of evidence as proof that nobody is out there, you should read it as proof that your survey is young, biased, and incomplete. You've confirmed that planets are common, which is step one. The steps where you actually identify serious candidates for alien homeworlds and then search for their fingerprints are only just beginning. And if your maps are this rough, there's another factor that makes the silence even less surprising. Your own position in the galaxy might be in a relatively quiet, out-of-the-way region, not in the densest traffic lanes where advanced civilizations, if they exist, would most likely cluster and travel. You know how we've been talking about distances and energy and filters like it's all abstract math? There's another piece that's much more basic. Where you live in the galaxy just might not be a busy place. Start with your address again, but this time in terms of galactic neighborhoods. The Sun orbits the center of the Milky Way at a roughly 25 to 27,000 light years. Remember, 1 light year is about 10 trillion kilometers, around 6 trillion miles. So you're sitting something like 250 quadrillion kilometers from the galactic center. You're not in the bright, dense core where stars are packed closer together, and you're not way out in the thin outer halo where stars are extremely sparse. You're in a spiral arm region that is relatively calm. That position has pros and cons. The pro is the environment is more stable. The core region, the inner few thousand light years, is busy and violent. More stars, more interactions, more supernovae, more radiation. Your distance puts you far enough away that you're not constantly blasted by that chaos. At the same time, you're not so far out that you're in a low-density desert of stars. So, on paper, it looks like a middle location. This fits into an idea called the galactic habitable zone. The concept is simple. Too close to the galactic center and you deal with higher radiation levels, more frequent nearby supernovae, and stronger gravitational disturbances. That makes it harder for stable planetary systems and stable biospheres to survive for billions of years. Too far out from the center, and you run into a different problem. Not enough heavy elements, what astronomers call metals, to build lots of rocky planets and complex chemistry. Stars farther out, on average, are more metal poor. So there's a ring at certain distances from the center where conditions are not too violent, not too poor in elements. That ring is the galactic habitable zone, and the Sun and Earth sit inside it. That's good for you. It means you had both enough materials and enough stability to form and keep a habitable planet for billions of years. But being in that zone doesn't guarantee anything about how many neighbors you have. It just means you're in a region where life has a better chance than average. Even inside that ring, the distribution of stars isn't uniform. Some regions are more crowded, with many sun-like stars closer together. Others, like where you are more spread out. So now think about where advanced civilizations, if they exist, would most likely cluster and move. If you're building interstellar infrastructure, it's cheaper and easier in areas where stars are close to each other, where the average distance between potential target systems is smaller. You get more options per unit of travel distance. That means dense star clusters, rich parts of spiral arms, or regions with many suitable stars packed into a relatively small volume are more attractive. Travel times are shorter, energy costs per hop are lower, and communication delays are reduced. Those become natural traffic lanes, places where interstellar routes, trade, exploration, or whatever passes for activity in an alien civilization concentrate. By contrast, a region like the Sun's neighborhood is more like a quiet, low-density area. Still stars around, still interesting, but not the optimal zone if you're planning an intensive network of interstellar paths. Think about how airlines operate. They don't build huge hubs in every small town. They focus on certain busy airports and routes. On a galactic scale, you may be located closer to the equivalent of a smaller regional area, not a main hub. Zoom out even further. On very large scales, astronomers have found that matter in the universe isn't spread evenly. Galaxies sit in filaments of dark matter and gas, huge structures tens of millions of light years long. These filaments connect into a cosmic web, with clusters and superclusters at the intersections. On those scales, you clearly see clumping, places where things are more concentrated. If civilizations tend to follow the distribution of matter in stars, it wouldn't be surprising if they also clump on smaller scales. Some parts of a galaxy might end up with many advanced civilizations over time, while others have very few. Your place in that distribution is unknown, but the lack of obvious signs around you suggests you're not in a crowded cluster of civilizations. You could be in a quieter patch that still qualifies as habitable, but isn't prime real estate for dense interstellar networks. So what does that mean for visits? If the densest civilization zones are somewhere else in the galaxy, then the bulk of any interstellar traffic, probes, or megastructures will appear there, not here. Ships will be launched between high-value systems first. Long-term projects will focus on regions with more stars and more resources. Only a small fraction of activity, if any, would spill over into lower priority areas like your local space. From your point of view, that translates to long stretches of nothing. Fewer ships, fewer probes, fewer artificial objects pass through. And when you combine that with the insane travel distances and energy costs we already talked about, the result is simple. There is no reason for your orbit around an average star in a relatively calm part of a spiral arm to see constant traffic. This is the same effect you see on Earth scaled up. Remote towns don't see international flights. Deep rural roads don't carry heavy global trade. It's not that the planet is empty, it's that most of the action is concentrated elsewhere and the edges stay quiet. In the Milky Way, your solar system may be one of those edges, far enough from the main streams of interstellar activity that you rarely, if ever, see the flow. Add that to all the other factors, and location alone becomes a strong reason for the silence. Even if the galaxy hosts advanced civilizations, if they are clustered far from you, your region naturally sees fewer visitors. No one needs to intentionally avoid you, they simply have more important destinations closer by, and physics pushes them to focus on those. So now the picture is this. You live in a large, sparsely trafficked neighborhood. You have limited listening tools, your maps are incomplete, and real interstellar missions are rare and expensive. Under those conditions, of course you don't see obvious visitors. The odds are stacked against you. But there's another twist. Even if a civilization did send something your way, even if it passed relatively close, you might still not notice because you're assuming visitors look like big metal ships and loud radio chatter. What if they use very different methods to move and communicate, ones your current sensors barely touch? You've been assuming that if anyone out there was talking or visiting, you'd notice, but that assumes their tech looks like your tech, just bigger. That's a bad assumption. Start with radio itself. Human civilization went from no radio at all to global radio to fiber optics and tight beam communication in about a century. That's nothing on cosmic time. Already, a lot of your high-value communication doesn't leak much into space. It runs through cables, focused microwave links, directed lasers, and short-range networks. If you keep going down that road, 1,000 years from now, your radio noise might be much lower than it is today. So think about a civilization that's a few hundred or a few thousand years ahead of you. Their loud radio phase might be over. Maybe they had a noisy period like you, then they optimized everything for efficiency and privacy. Almost no broadcast leakage. Almost everything is tight beam or wired. If you're expecting them to light up your radio telescopes the way your early TV and radar do, you're looking for the wrong thing at the wrong moment in their timeline. Then ask how they might actually communicate over interstellar distances if they're serious about it. You know about a few options already, at least in theory. One is ultra-tight laser beams feared between specific points, potentially in optical or near-infrared bands. Very high data rates, extremely directional, almost invisible to anyone who isn't sitting directly in the beam. Another option is neutrino communication. Neutrinos barely interact with matter, so they pass through almost everything. That makes them hard to detect, but also means you can, in principle, send messages straight through stars and planets without worrying about blocking. Building neutrino transmitters and receivers at that scale is beyond you right now, but it might be trivial for a very advanced species. Even more exotic, gravitational waves. You already detect them from colliding black holes and neutron stars. In theory, you could encode information by moving huge masses in controlled ways. It sounds like pure science fiction for you, but for something that's been engineering at stellar scales for millions of years, it might be just another channel. So while you're pointing big dishes at the sky, listening for broad, continuous radio signals, a truly advanced civilization might be using lasers so tight you'd have to be in exactly the right line of sight. Neutrinos you barely detect at all, or engineered gravitational ripples you have no hope of decoding. You're basically checking the AM bands while the universe, if it's talking, has moved on to encrypted fiber and beam lengths. Now think about how they might travel. Your picture of aliens visiting is dominated by huge starships, big metal craft with crews, maybe some kind of science fiction drive. But if you care about physics and energy, the smarter move is the opposite. Keep things as small and fast as possible. A very advanced civilization might build gram-scale probes about the mass of a paperclip with integrated sensors, computation, and maybe tiny sails. Push them with powerful lasers or fusion drives up to a good fraction of light speed, say around 20%. At that speed, they cover 1 light year in roughly 5 years. Crossing the distance to a nearby star system takes a few decades, not tens of thousands of years, and you can send swarms of them. From your side though, what does that look like? You have a tiny object, grams of material, moving at tens of thousands of kilometers per second, tens of millions of miles per hour. Your current telescopes are not built to spot that. Your radars are focused on near-Earth space and slow objects. Something that small and that fast zips through your system, maybe does a flyby, maybe parks in a distant stable orbit around the sun, and you never notice. It's invisible in the noise of asteroids, comets, and instrumental limits. And you already have a track record of misclassifying strange signals. Take fast radio bursts, FRBs. When you first found them, they were mysterious, brief, intense radio flashes from distant galaxies. For a while, people seriously asked, could these be artificial? As data improved, most FRBs turned out to be natural, likely from extreme astrophysical events. But the key point is this. Your first reaction to weird signals is confusion, then probably natural, unless you have overwhelming evidence otherwise. If an engineered signal doesn't look exactly how you expect, it can easily end up in a category labeled odd transient, instrumental artifact, or unidentified but likely natural. Your pipelines, your filters, your human habits all push you to assume nature first. That's reasonable, but it also means any subtle or cleverly encoded technosignature could be hiding under labels you've already filed away as unimportant. Combine all of this, and you get a very different view of no one has visited. It might not mean empty space. It might mean that whatever is out there is using communication modes that blend into background noise and sending probes that are too small, too fast, or too well hidden for your current tools. They could have passed through the outer solar system centuries ago, dropped a tiny observer onto a dark rock in a distant orbit, and settled in to watch, with you completely unaware. From your perspective, that is indistinguishable from "no one is here." The instruments you have, the frequencies you monitor, the objects you track, all define a narrow slice of reality. Anything outside that slice might as well not exist to you, even if it's literally in your cosmic backyard. So if physics, energy, and stealth all push advanced civilizations toward quiet channels and tiny hardware, and your detection tools are still crude and biased, the lack of recognized visits is exactly what you'd expect. And that brings you to one more uncomfortable possibility. Maybe some civilizations don't just stay quiet for efficiency. Maybe they stay quiet on purpose, because they've learned that announcing yourself loudly in a dangerous universe is a very bad idea. You've been assuming that if no one shows up, it's because no one is there or no one can reach you. There's another angle that's colder. They might be able to reach you just fine and be choosing not to. Start with the dark forest idea in simple terms. Picture a universe where resources are finite, where you can't be sure of other civilizations' intentions, and where technology can turn a small advantage into total domination. In that setup, game theory says the safest move is ugly. Stay quiet, hide your location, and if you must act, strike early against anything that looks like a potential threat. Don't trust anyone, don't announce yourself, and treat loud newcomers as dangers, not friends. In that kind of galaxy, broadcasting, "Hi, we're here, this is our exact position," is not friendly, it's reckless. It's like switching on a giant spotlight in a place where you don't know who else is watching or how they behave. From that perspective, your last 100 years of radio noise and radar blasts look less like a natural step and more like a risky move from a species that doesn't yet understand the rules of the wider game. You can already see a weaker version of this logic in your own behavior. When humans encounter an uncontacted tribe or a fragile ecosystem, you don't just barge in casually anymore. At least not if you're thinking clearly. You argue about whether to make contact at all, whether to leave them alone, whether exposure to your diseases, your technology, your culture will destroy what's there. History shows that contact often goes badly, especially for the weaker side. Colonization, exploitation, cultural collapse all happened here on one planet with one species. Scale that up. An advanced civilization that's been spacefaring for millennia might have made contact with others before and watched those encounters turn into disasters, even when they meant well. They might have hard data that says direct contact tends to destabilize younger societies, and sometimes they react violently. After enough bad outcomes, a rational, long-lived civilization might adopt a strict rule: do not interfere. Watch, record, maybe nudge indirectly at most, but never openly land and announce yourself, because the risks outweigh the benefits. That leads straight into the zoo hypothesis. The idea is simple. Earth might be inside a kind of preserve. If a network of older civilizations has decided that young species should be left to develop on their own, then you would expect exactly what you see now. No landings on the White House lawn, no obvious ships hovering over cities, no broadcast that says, "Welcome to the Galactic Federation." Any visible, undeniable contact would break the rules of the park. In that scenario, there could be observers parked in stable orbits far from the sun, or tiny probes hidden in places you haven't searched well. They would camouflage themselves, avoid obvious interference, and only watch. They might have strict protocols against altering your culture or your technological path. From inside the preserve, you would have no direct evidence they exist, by design. You can't prove that's happening, but here's the key. Your actual observations so far are consistent with it. Look around the solar system. With the telescopes and spacecraft you currently have, you don't see unambiguous signs of tampering. No obviously artificial objects in simple, stable solar orbits that scream, "This is a giant alien station," at the resolution you can see. No moons covered in visible city lights. No megastructures around the sun re-radiating most of its light as waste heat in a way you can't explain naturally. That lack of clear, in-your-face engineering is compatible with no one has ever been here. But it's also compatible with someone is here and they follow a strict non-interference and stealth policy. If they are much more advanced than you, hiding from your current level of sensors is not hard. You don't have the resolution or the coverage to rule out small, dark, cleverly parked devices. All you can honestly say is, we haven't seen obvious large-scale artifacts. So ask what an intentional silence policy would feel like from your side. You'd grow up hearing only your own broadcasts. You'd send probes and telescopes out, see nothing clearly artificial, and conclude the galaxy is empty. No one would land. No one would handshake with your governments. No one would hijack your TV feeds. Everything would look exactly as it does to you now. If the galaxy default among older civilizations is observe but never interfere, that's the only reality you'd ever experience. You would live and die without seeing a single undeniable visitor, even if your system had been under quiet observation for centuries. The absence of loud, obvious contact is not evidence against the non-interference rule, it's exactly what that rule predicts. Of course, there's an even darker version of this logic. If some regions of the galaxy behave like a dark forest, where the safest move is to remove potential threats before they become dangerous, then any young, noisy civilization is in trouble. But even in that case, it still makes sense for most players to remain unseen and cautious. Loud, open contact is rare. Stealth, ambiguity, and distance are normal. Either way, whether it's a protective zoo ethic, a paranoid dark forest, or some mix of both, the result for you is the same. You don't see visitors. You don't hear clear messages. You only see your own reflection plus natural cosmic noise. Intentional silence looks identical to absence from where you're standing with your current tools on your current timeline. And if you add one more ingredient, the universe's own habit of throwing massive disasters at planets and stars, you get an even tighter picture. Not only might civilizations avoid you on purpose, most of the ones that ever formed might have been wiped out long before they got the chance to come anywhere near you. You've seen that distance, energy, and bad timing all work against visitors, but there's another rule the universe keeps applying over and over. It keeps trying to wipe the board clean just when things get interesting. Start with supernovae. Big stars don't die quietly, they explode. When a massive star runs out of fuel, its core collapses and the outer layers blast out as a supernova, dumping huge amounts of energy and high-energy radiation into surrounding space. If that happens within a few tens of light years of a life-bearing planet, it's bad news. The radiation can punch holes in the ozone layer, let more ultraviolet light from the star reach the surface, and push mutation rates up. You can trigger climate changes, mass die-offs, and long periods where complex life struggles to recover. Over billions of years, a lot of star systems will have at least one of these events happen uncomfortably close. Some will just get stressed. Others will get almost sterilized. If any of those planets were in the middle of evolving complex ecosystems or early civilizations, a nearby supernova can reset that progress or erase it completely. Evolution has to start rebuilding, slowly, from whatever survives. Then there are gamma-ray bursts, GRBs. These are even more extreme. They're thought to come from very rare events, like the collapse of especially massive stars, or mergers of compact objects, and they fire focused beams of gamma radiation across space. If your planet sits in the path of one of those beams, even at thousands of light years, the energy dump is enough to seriously damage the atmosphere and biosphere. A single gamma-ray burst can undo hundreds of millions of years of gradual evolution in a burst that lasts seconds to minutes. It doesn't care if your world has just reached the stage of complex marine life, forests, or even early tool users. The physics is the same. If you're in the wrong place at the wrong moment, you get hit, and the entire evolutionary trajectory changes or collapses. You go from maybe on track for future civilization to whatever hardy life can cling on after the disaster. Earth itself has felt the universe's smaller punches directly. You have a clear record of impact events and mass extinctions. The most famous one is the one that killed off the non-avian dinosaurs about 66 million years ago. That impactor was on the order of 10 kilometers across. It hit with an energy yield equivalent to many billions of megatons of TNT, set fires over huge regions, kicked dust and aerosols into the atmosphere, and disrupted climate enough to reshuffle the planet's dominant life. Now scale that up. A 100-kilometer object delivers energy on the order of tens of millions of megatons. An impact like that doesn't just knock back big animals, it can strip away parts of the atmosphere, boil oceans locally, and melt large sections of crust. If a young technological civilization had built cities and infrastructure, that kind of event could erase almost every trace on the surface. Species might survive in refuges, but the entire technological layer would be gone, and climbing back up isn't guaranteed. There are also slower but still dangerous forms of instability built into stars and planetary systems themselves. Not all stars are as relatively calm as the Sun has been during human history. Red dwarfs, which we talked about earlier, can flare violently, repeatedly stressing atmospheres and biospheres. Massive stars burn hot and bright but die young, giving their planets less time to evolve complex life before the star itself ends things. On the planetary side, orbits in multi-body systems can be chaotic over long timescales, especially if there are large planets or passing stars. A planet that looks comfortably stable on million-year scales might drift into a more eccentric orbit over hundreds of millions of years, leading to extreme ice ages or runaway greenhouse phases. Tidal interactions can lock planets, change rotation rates, or heat interiors enough to drive intense volcanism. A system that looks habitable at one snapshot in time might have spent most of its history in states that are hostile to complex long-term life. When you put all of these factors together, a pattern emerges. The universe is not sitting there politely giving every planet a clean, uninterrupted window to evolve brains and spaceships. It throws radiation events, impacts, flares, orbital shifts, and climate swings at them again and again. On some worlds, life never gets past microbes. On others, complexity arises and is wiped out multiple times. On a few, maybe, evolution threads the needle, getting enough stability for long enough to produce a technological species. That means long-lived spacefaring civilizations are not just the next step after life, they're the exception. They are the rare cases where a planet's environment stayed within certain bounds for billions of years, where evolution made a series of hard jumps, and where that technological species then survived its own disasters long enough to start building serious space capability. That's a lot of conditions stacked on top of each other. From the perspective of why hasn't anyone visited, this matters a lot. Every time a region of the galaxy gets hit by a nearby supernova or a gamma-ray burst, any evolving biospheres in that zone get slammed. Some are knocked back to simple life, some might be sterilized. Potential civilizations that might have existed there 10 or 100 million years later never appear. Their line is cut before it starts. Even on worlds that do get civilizations, big impacts or stellar changes can end them before they reach interstellar travel. So your list of potential visitors shrinks not just because life and intelligence are hard, but because the universe is constantly running a delete function on entire timelines. The ones that make it far enough to launch interstellar probes are the survivors of multiple rounds of cosmic selection, not the average outcome. The quiet sky above you could therefore be partly a graveyard effect. There may have been many planets that almost produced travelers, that built early technology, that looked up and wondered about the stars, and then got hit by something they couldn't avoid. Their ruins, if they exist, are light years away, eroded, buried, or frozen, and you don't yet have the tools to see them. In that context, a lack of visitors is exactly what you'd predict. Most potential guests never get a real chance. They keep getting knocked back to zero by physics, by random events, by their own unstable environments. Only a tiny fraction get far enough, fast enough to matter on interstellar scales. And there's one more twist. Even among those rare survivors that do reach extreme levels of technology, some may decide that planets like Earth, with air, oceans, and fragile biology, are not where the real action is anymore. They may have moved on to a very different kind of existence, where visiting a surface world is not a goal at all. Start with the basic shift. Once a species can build general AI and robust robotics, it has the potential to move most of its thinking out of wet brains into machines. Biological brains are amazing, but they're fragile. They need narrow temperature ranges, specific chemistry, constant supply chains of food and oxygen. Hardware minds can, in principle, be tougher, more efficient, and much more flexible about where they operate. From that point of view, living on a planet is not the ultimate goal, it's the starting condition. A surface world with weather, earthquakes, volcanoes, storms, and impacts is a risky environment. To a mature machine civilization, clinging to a gravity well with random disasters might feel like living in a flood-prone shack when you have the option to build hardened facilities in stable, controlled environments off-world. Now add in one important piece of physics. Computation works better in the cold. When you process information, you generate heat. The cooler your surroundings, the easier it is to dump that heat, and the more efficiently you can run your systems for a given amount of energy. That means a machine-based civilization that cares about maximizing thinking power per joule is incentivized to move away from hot, bright, messy zones. Where is it cold and dark? Not near stars like the sun, and not deep in the crowded, glowing core of the galaxy. The sweet spots for efficient computing are the outskirts of galaxies, far from intense starlight, or even the spaces between galaxies, where the background temperature is only a few degrees above absolute zero. Those are terrible places for biology, but perfect for vast computer structures. So the things that are good for origin of life planets are not necessarily the things that are good for ultimate machine civilizations. You expect life to start near stars like the sun. You might expect advanced post-biological societies to drift outward over time into colder, quieter, darker zones. Their centers of activity move away from where you're looking. You've tried to search for these huge, loud versions by looking for megastructures. One idea is a Dyson sphere or Dyson swarm, a collection of structures that capture most of a star's light and re-emit it as waste heat in the infrared. Astronomers have scanned catalogs of stars, checking for those with unusual infrared signatures that might mean this star is wrapped in technology. So far, there are interesting oddballs, but no clear galaxy-spanning examples where you can confidently say this is definitely artificial. On the scale of entire galaxies, you don't see systems where most of the starlight is clearly being soaked up and re-radiated as heat by industry. That suggests either of two things. One, truly large post-biological civilizations are extremely rare. Or two, they do exist, but they're much more subtle and efficient than your simple Dyson sphere mental picture. Maybe they use stars sparingly. Maybe they spread their infrastructure thin. Maybe they've optimized to the point where the waste heat you'd expect is too faint or too well hidden for you to pick up at your current sensitivity. Either way, it undercuts the idea that, if they were out there, the sky would obviously look artificial. You've looked for the loudest, clumsiest version of that and haven't seen it. That doesn't rule out quiet, advanced versions that don't match your early expectations. Now, ask what such a civilization would think about Earth. If their main interests are maximizing computation, exploring virtual realities, running simulations, or manipulating matter and energy directly at fine scales, a wet biosphere around a G-type star is not a prime objective. It's a historical curiosity. It's an interesting data point in the early stages of life, the way you might think about ancient shallow seas on your own planet. For them, the cost of sending physical hardware into a deep gravity well, through a thick atmosphere, down onto a surface covered in salt water and organic muck, just to interact with a species that's maybe a few hundred years into serious technology, might not make sense. The risk, the energy, and the time might not justify the payoff. From their perspective, visiting Earth physically could be like a modern human trekking across a continent to shake hands with one particularly interesting bacteria colony in some random pond. You could do it, you probably won't. If you care about microbiology, you take samples, you run tests, maybe you watch from a safe distance. You don't redesign your whole life around direct contact. So you get a strange situation. The cosmos could be full of minds, in the sense that there could be many advanced post-biological civilizations spread across galaxy halos, intergalactic filaments, and cold outer regions. They might be running unimaginable amounts of computation, doing whatever counts as high-level activity at their stage. But their playground is not the surface of planets like yours. Their attention is focused where their infrastructure is, and that is not here. In that scenario, the reason you haven't seen visitors is almost embarrassingly simple. You're not the point. You're in a phase they passed a long time ago. Planets were interesting when life was starting out, when evolution was still discovering complexity. Once they move into the machine era, their center of gravity shifts. The messy, warm biological layer is something they keep in their records, not something they actively travel to. From your vantage point, this all folds into the same observational reality. No megastructures you can clearly see, no giant ships, no obvious signals. Whether that's because such civilizations are rare or because they're post-biological and operating in regions and modes you don't track, the end result is the same. Planets like Earth are not where the main action is anymore. And that brings you to a final, unsettling possibility. After pulling together all of this, the distances, the energy costs, the filters, the disasters, the tech gaps, the quiet strategies, and the post-biological paths, you might have to accept that in your local patch of space, there really might be no one else at your level or above. Not hidden, not just quiet, but genuinely absent within any practical travel range. Start with the anthropic argument in plain language. You exist because you're on a planet where things lined up just right for observers to appear. That does not mean those conditions are normal, it just means you had to wake up in a place that works. You do not get to see all the dead planets where life never started, or stalled at microbes, or died out before it got clever. You only ever see the one where things went unusually well. So, when you ask, where is everybody, the fact that you are here to ask that question doesn't guarantee there is an everybody out there. You're a data point, not a crowd. You know that at least one planet, yours, produced a technological species. That's it. Everything else is an inference and a hope. Now, look at the biggest, loudest things you might expect to see if extremely advanced civilizations were common. On the Kardashev scale, a Type 3 civilization uses most of the power output of its entire galaxy. That would mean massive engineering on stellar scales, lots of stars wrapped in collectors or reorganized in obvious ways, or whole regions of a galaxy dimmed and glowing strongly in infrared from waste heat. When astronomers scan the sky across the observable universe, they don't see clear cases of that. Galaxies look like galaxies, spiral, elliptical, irregular, with star formation and dust and gas that match the predictions of physics. No galaxy has popped out as, this entire thing is clearly being hijacked by someone turning stars into hardware. If Type 3 civilizations were all over the place, you'd expect at least a few really obvious anomalies. You don't see them. Zoom out even more. Recent observations have mapped enormous rotating filaments of galaxies and dark matter, structures tens of millions of light years long, forming a cosmic web. Their shapes, motions, and distributions match what you get from simulations that only include gravity, normal matter, and dark matter. On these scales, you do not see clear signs of artificial reshaping. No straight lines of galaxies, no regular grids, no patterns that scream designed. You see nature, not visible engineering. Then come back down to the scales you actually care about for visitors. You have more than 6,000 confirmed exoplanets in your catalogs, and the real number across the galaxy is in the hundreds of billions. Most of the ones you've studied properly do not look like Earth. They are hot Jupiters, mini Neptunes, super-Earths with unknown surfaces, planets with questionable atmospheres. Out of the few you can probe in detail, comfortable Earth-like surface with long-term stability does not dominate. On top of that, you've looked for techno-signatures in nearby space. Projects like Breakthrough Listen and other SETI efforts have scanned thousands of stars within a few hundred light years across a range of radio frequencies looking for narrow, artificial transmissions. You have not found a convincing, repeated, structured transmission that holds up after checks for interference and natural explanations. That doesn't rule out everything, but it does tell you that in the closest 1,000 or so stars you've checked, there isn't a loud, always-on beacon screaming in standard radio. And you've searched for megastructures on more modest scales too, checking for stars with odd infrared excess that could hint at Dyson swarms, at least in bulk. You found interesting systems, dust shells and weird disks, but nothing you can point to and say, this is definitely a star wrapped in artificial collectors. So no clear Type 2 or Type 3 examples nearby, and no obvious galaxy-scale cases far away. Put those pieces together. You see a universe full of planets, most of them not very friendly to your kind of life. You see no clear galaxy-scale engineering. You see no undisputed techno-signatures in the closest 1,000 or so stars you've examined. You see no giant obvious artifacts in your own solar system. That set of facts is still completely consistent with a picture where advanced civilizations exist, but are extremely rare and very widely spaced. Extremely rare here could mean something like one spacefaring civilization per huge chunk of the galaxy, separated by thousands or tens of thousands of light years. That is still not zero, but it's sparse enough that within a radius you can realistically reach or talk to with current or near-future tech, there might be nobody else. Think of a sphere a few thousand light years across around the sun. That volume contains millions of stars, but if the average spacing between technological civilizations is bigger than that, then your bubble has only one: you. If that's how things are, then no one has visited might literally be true, not just for the last few thousand years, but for the entire history of life on Earth. Not because the galaxy is dead, but because you're sitting in a patch of space where you are the only technological species for a very long distance in every direction. In that case, the reason no one has dropped by is the same reason no one has visited a random rock on a random island on a random planet. There simply isn't anyone else nearby with both the ability and the knowledge to do it. And this is where all the different arguments start to line up. The size of the galaxy, the speed limit set by light, the huge energy costs of interstellar travel, the narrow window where a civilization is both advanced and stable, the constant risk from disasters, the possibility of great filters, the absence of obvious megastructures, the incomplete maps, and the chance that post-biological minds aren't interested in planets anyway. None of those alone absolutely prove you're locally alone. Together, they make that scenario very hard to dismiss. So you end up with a simple but heavy conclusion. In your part of the Milky Way, right now, you might really be it. No older siblings about to step in, no galactic government on standby, no backup civilization waiting to catch you if you fall. If that's the case, then the quiet sky isn't just a mystery, it's a warning. Because if no one else is coming, all of the responsibility for what happens next in this region of space lands directly on you. So here's the hardest possibility to swallow. No one has come because no one else can, and if anything is ever going to move out across this part of the galaxy, it has to start with you. Think about what that actually means. All those filters we talked about, the hostile planets, the slow evolution, the disasters, the energy limits, maybe they all stacked in your favor once, right here. You got a stable G-type star, not a flare-crazy dwarf or a massive short-lived furnace. You got the right orbit, not too close, not too far. You got a long sequence of rare biological jumps, from simple cells to complex cells, to multicellular life, to nervous systems, to technological intelligence. You dodged nearby supernovae, gamma-ray bursts, and planet-killing impacts for just long enough. If that full chain is rare on galactic scales, then you're not just another civilization among thousands. You're the civilization in a huge volume of space. Within hundreds or thousands of light years, you might genuinely be the first species to reach this level. That thought should scare you and thrill you at the same time. It means your decisions on this one planet could set the tone for everything that ever happens here in the future for millions of years. Now layer on the clock you're living under. The sun is stable by human standards, but it's not frozen in time. As it burns hydrogen in its core, it slowly gets brighter. It will stay on the main sequence for about another 5 billion years, but comfortable for complex life like yours is a narrower window. As the luminosity creeps up, Earth's climate will eventually shift. On geological scales, you're probably talking a few 100 million to maybe a couple of billion years before the planet gets significantly hotter in a way that makes advanced life struggle. To you, 100 million years sounds infinite. Your whole recorded history is a few thousand years. Your industrial era is under 200 years. But for the star and the galaxy, 100 million years is a slice. It's long enough to matter, but not long enough that you can just drift and hope. Every delay you build in now, every century you waste in stalemates and self-inflicted crises, eats into that window. Now, look at what you've actually done so far in terms of reaching out. Your true physical footprint in space is tiny. Your strongest radio and TV signals, your radar pulses, have been traveling for only about 100 years. That gives you a radio bubble about 100 light years across, which is nothing compared to the 100,000 light year width of the Milky Way. Your hardware presence is even smaller. Voyager 1, your most distant probe, is a bit under 26 billion kilometers from Earth, on the order of 1 light day or so from the Sun. In miles, that's around 16 billion miles. In linear terms, that's impressive. In galactic terms, it's basically still on the front porch. Almost all of your matter, all of your industry, all of your culture is still sitting in a thin film on the surface of one planet, plus a handful of tiny machines drifting just outside the outer edge of one solar system. If nobody else is coming, growing that footprint is 100% your responsibility. There is no older civilization scheduled to arrive and hand you a star map, no one queued up to drop fusion drives and perfect life support in your lap. If interstellar travel is ever going to happen here, it has to be designed, built, and paid for by you, starting from chemical rockets and fragile electronics, climbing up step by step. This is where the silence stops being just a curiosity and starts changing the stakes. If the galaxy feels empty because travel is hard, the filters are brutal, and technological intelligence is rare and fragile, then your survival and expansion stop being just human issues. They become a unique event in this region of space. If you wipe yourselves out or stall permanently, your entire local patch of the galaxy might stay quiet until the sun dies, or until some totally different line of evolution gets lucky on some other world, millions or billions of years from now. "No one has visited" then reads like a warning label, not a snub. It means there is no backup, no second attempt already underway on a nearby planet, no safety net waiting off stage. If you fail, the story here ends, at least for a very long time. If you succeed, almost everything that happens next, exploration, colonization, transformation, will trace back to the choices of a species that, right now, still struggles to keep its own atmosphere stable and its own members from fighting on a global scale. So what exactly is your role in all of this? You don't get to be a background character. You're a young civilization sitting on a rare, working platform in a dangerous universe, with a shrinking but still huge amount of time in front of you. From here, there are only a few broad paths. You can collapse through war or environmental damage or uncontrolled technology. You can stagnate, locking yourselves into a long plateau where you never quite manage to break out of the solar system in a serious way. Or you can decide that since no one else is coming, you will be the species that carries life further out. Crossing 4.25 light years to Proxima Centauri suddenly stops being a fun sci-fi scenario and becomes a test of whether you can take the first real step away from total vulnerability. Building the ability to move reliably between stars, even on timescales of decades or centuries, becomes not just an engineering challenge, but a survival move for your entire branch of life. Extending your footprint to multiple systems over thousands or tens of thousands of years turns into the only way to make sure one bad event doesn't wipe out everything that asks questions or builds telescopes in this part of the galaxy. And that effort, if it happens, doesn't start with heroic starships in some distant future. It starts now, with how you handle your own energy use, your climate, your technology risks, your conflicts, your science funding, your long-term planning. It starts with whether you treat space as a stunt or as the core long-term project of a civilization that realizes it might be the only one around for a very, very long way. So when you wonder why no one has come to visit, one answer is harsh and simple. There was no one else available. The universe cleared a narrow path here once, and you walked onto it. What happens next is not waiting on them, it's waiting on you. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.